let's talk about Cauchy Schwarz inequality. Suppose you have two vectors u and v in Euclidean space Rn. Then the absolute value of the dot product between u and v is less than or equals to the magnitude of u and magnitude of v. Let's take a look at the proof. If one of these two vectors is 0, if u is equal to 0 or v is equal to 0, then 0 that any vector is 0, the magnitude of 0 is also 0. So left-hand side is 0, right-hand side is 0, 0 is equal to 0. We don't have anything to prove. Now suppose these vectors are non-zero vectors. We're going to come up with a creative idea. We're going to connect linear algebra with intermediate algebra, quadratic equations. Let t be a real value. Form t u plus v, a linear combination of these two vectors, and find the dot product. So this is what is happening here, and find the dot product, tu plus v. This guy is equal to, based on what we learned before, this is t squared u dot u plus tu dot v plus tv dot u plus v dot v, which we can simplify as t squared u dot u plus t u dot v plus t u dot v. It's commutative, plus v dot v. This guy can be written as t squared u dot u plus 2t u dot v plus v dot v. For simplicity, let us call these A, B, and C. So basically you have a t squared plus 2bt plus c, which is a quadratic equation. Again, recall that from intermediate algebra, that if you have ax squared plus bx plus c, we have three scenarios. If b squared minus 4ac is positive, then the graph crosses x-axis. If b squared minus 4ac is equal to 0, then you only have one intersection with x-axis. If b squared minus 4ac is negative, then there is no intersection with x-axis. But take a look at this quadratic equation here. This guy is always larger than or equal to 0. What's the meaning of that? It means that it is either having just one intersection or it has no intersection. So 4b squared minus 4ac is always less than or equal to 0. 4b squared minus 4ac, just 4 should be outside, less than equal to 0. Or you have b squared less than equals to ac. But what is b? b is u dot v. So you have u dot v to the second less than equals to a, which is u dot u, and c, which is v dot v. If you take square root of both hand sides, you get absolute value of uv less than equals to, here you have the dot product between u and u square root, which is basically the magnitude of u, the dot product between v and v, and taking the square root gives you magnitude of v. Again, the square root of u dot u is basically finding the magnitude of u, and the square root of v dot v is basically the magnitude of v. Now remember, when you're taking the square root of u dot v to the second, it's always equal to absolute value of u dot v. So we just proved the Cauchy Schwarz theorem.